Hi, I'm Rohan Bull, and this is my Lab 4 Circuits and Capacitors presentation. So, starting with the overview and the purpose of this lab was to help us understand the principles of conservation of energy, the loop rule, and current conservation. An overview of this is we will use a FET simulation on circuits to help us visualize how resistors and capacitors work in action. Some of the principles used are the loop rule, which states that the total potential difference around a closed circuit is zero. The node rule, where the current flowing in is equal to the current flowing out. Capacitance, which is charge over voltage. And Ohm's law, which is voltage equals current times resistance. So starting with the base circuit, we have two 1.5 volt batteries, two ammeters, and two resistors. One that's 47 ohms, the top one, and one that's 100 ohms, the bottom one. As you can see, the ammeters say the current is 0.02 amps, which can be calculated by rearranging Ohm's law, where current can equal volt over resistance, so 3 volts over 147 total ohms is 0.02 amps. The reverse, if we reverse the ammeters, we get negative 0.02 amps. Part 2 states us to replace one of the ammeters with a voltmeter. And the voltmeter reads 3 volts, because that should be the total. The ammeter reads 0 amps because it is an open circuit. Next part asked us to put an ammeter parallel to the 100 ohm resistor. And as you can see, this increases the total amps to 0.06 because some of the current is going around the 100 ohm resistor through the ammeter and therefore increasing the flow. So at the top left is a chart, a graphical representation of the volts. So from points A to B, the two batteries, it charges up to 3 volts. So sorry, the voltage is up to 3 volts. B to C is stagnant. C to D, it goes down, and that is through the 47 ohm resistor. D to E stagnant. E to F, it goes all the way down to 0 through the 100 ohm resistor. And from F all the way back to A, it stays 0. Beneath that is a numerical representation of the graph, where AB is 3 volts, CD is negative 0.959, and EF is negative 0.2041. At the top right, if you sum up all of the voltages, it adds up all back to 0, which satisfies the loop rule. And beneath that are the calculations for the resistors. The 47 ohm resistor came out to be 47.95 ohms, 100 ohm resistor 102.05 ohms, and the wired ammeter 0 ohms. I can attribute the miscalculations due to inaccuracy in the simulation. The next part asks us to replace everything with light bulbs and capacitors. One 9-volt battery, a capacitor, and a 10 ohm light bulb and a 20 ohm light bulb. These form an RC circuit, and these are my observations regarding it. The light dims quickly and turns off. The light dims with the capacitor connected. The current slows to a halt, and the current is reversed with no battery connected. The time beneath that is the times we were asked to record. For the 10 ohm bulb, it takes 19.74 seconds to charge up and 19.68 seconds to discharge. I can assume that these times are supposed to be the same, however, due to human error, they are not. With the 20 ohm bulb, it takes 39.24 seconds to charge up and 39.21 seconds to discharge, roughly double the 10 ohm bulb. This is the data that I recorded. As you can see, when plotting the ln graph, it forms a straight line, which we can use to calculate the RC, which is -1 over the slope of the discharge rate. So -1 over negative 0.167 equals 5.988. Reflection questions. What if I were doing this lab in real life? What's different about a real ammeter? And how would it have affected which circuits I hooked it up to? And an ammeter in real life would actually put up a small amount of resistance. Therefore, the amps would actually be smaller. And affecting which circuits I hooked it up to, it would be probably more limited. What if I were using a real battery to charge a real capacitor with no resistance? And would the prediction of the ideal model occur in real life? No, it wouldn't, because an ideal capacitor would be near instantaneous. However, it would take a bit of time in real life. Sorry, an ideal capacitor would be instantaneous.